Hello guys, thanks for having us here. Warm greetings from Prague. My name is Michael Löffler, here is Arce Franz. We are from OCCAM. OCCAM is abbreviation, I mean you know all the name. We just try to find a perfect acronym for that. Odessa Competence Center for Artificial Intelligence and Machine Learning. It sounds like super fancy, but we just had to fit it in the name. We'd like to present you today our approach to artificial intelligence and machine learning. And first we will have just very short introduction about ourselves. Then Arce will go into the big overview of our mathematical framework that we have in background about the incremental compression. AIXI will be part of this part of the presentation. We will also especially try to relate afterwards the connections between what we do and what you did before. So we try to pinpoint all the table of content that you had in your presentation, in your framework, and relate it step by step to what we did there. And afterwards I will give a short overview of what we did in the last year and the last month. We recently just started to actually do some programming and not just the mathematical part, and describe where we just stand right now, and also how this algorithm works behind the scenes. And afterwards we will have some outlook together. So we are located in Odessa on the Black Sea in Ukraine. OCCAM itself doesn't have any big clear goal to commercialize it right now. I mean, it may change at some point when we say, okay, just like we heard before, customers come up and say, okay, can you please help us there maybe? Or if you have something that kind of cries for an application, okay, maybe. But right now we just focus on getting the research done and forward. We have a small team, 3 mathematicians, including Arce, programmers, including me, and some help assistants around. Arce is doing artificial intelligence already for quite a while, already since university and probably even longer. But we kind of just started in end of 2017 to really form it and make it official, get some branding, hire some people for the project. And of course we're welcome for collaboration, and that's why we're here. And with that I would like to give this presentation to Arce.
Okay, thanks. So I would like to summarize our approach at this slide. First, I've heard you've had a quite similar definition of intelligence. There are many around: the ability to solve problems in a wide range of environments. Otherwise, of course, we don't want to build narrow AI. It's also it's a focus on the general AI. So, as some of you might know, a theory of universal intelligence exists developed by Markus Hutter. One of the formalizations or agents is called AIXI, and essentially it's a mixture of Solomonov's theory of universal induction and plus reinforcement learning. So the goal at OCCAM can be actually boiled down to trying to make universal induction efficient. This is kind of, we don't have a detailed roadmap, but there's it could be summarized. We think that if you solve the induction/compression problem, they're quite similar to each other. This will solve a large part of the path to AGI. And this is formulated quite bluntly now into the space. And I will during the talk I will try to substantiate that claim a bit more, during first relating it to AIXI and also relating it to what I understand is being done at GoodAI. And we believe that algorithmic information theory is the appropriate description language for intelligence. And which gives also the mathematical underpinnings of the theory. And essentially the goal is to write a monolithic, more or less monolithic, theory-driven, efficiently implemented algorithm for AGI. So I mean they're essentially what could maybe summarize, it's like or some approaches are like cognitive architectures that try to piece together many different parts. We try to write one good algorithm, and there are of course pros and cons to any of those approaches, but we can discuss it later then. So first, the motivation. You all probably know the difference between narrow and general AI, and I think it's quite nice to motivate it in that kind of graphic, where if you look at all the task space of all problems, and here's complexity and diversity, you would probably put the set of problems that can be solved by a typical machine learning algorithm is like a thin stripe that gets broader there. And that means that it can solve not a very diverse set of problems. Some few are simple, but most of them are very, very complicated. And that's why we need those algorithms, because they're better than humans, and then they can help us to solve particular tasks. And nevertheless, they're narrow, so you would want, for general AI, you want to fill the whole space somehow. And so what can you do? You can try to broaden that narrow algorithm, but usually you get into combinatorial explosions, which is the curse of dimensionality that everybody knows, that's the plague of the whole field of machine learning. And this is something you have to put many thoughts into in order to ask yourself, so how shall we solve it? And usually if you try to make an algorithm, if it does something simple, then you try to broaden it, it quickly moves up to the high complexity sphere, and there the space is just huge, and most instances have high complexity, and therefore a priori don't have a big probability of being the right solution. So it has the tendency of wandering in big spaces where finding the solution is not so probable. And so the orthogonal kind of approach is to think of general AI as some approach that tries to fill the task space broadly, to build an algorithm or a set of algorithms that fills it out and solves a wide range of simple tasks, maybe even all simple tasks. And and this is what humans seem to make. Humans cannot solve too complex tasks. That's why we have computers for it. But somehow, whenever you look at a machine learning algorithm, as soon as you understand it, it's easy to come up with an example that the algorithm will not be able to deal with. That's when you in practice, when you see that, it's easy, and somehow it comes from your brain, and that means your brain is able to represent that example, and somehow we are able to wander around in that diverse space as humans. And we're able to deal with all those examples. And while machine learning algorithms usually cannot. So the big question is, how does it happen? And how can we build an algorithm that can do it? And how can we build an algorithm where we cannot a priori say that here is an example that it will not be able to solve or to represent? Because whenever we think of a particular one, immediately there is an example that it cannot solve. So is there a way to approach that? In theory, there is a way. It's called universal search, or Relevance search. You just enumerate all possible programs and sort it by their lengths and execute them. So you will be guaranteed to find the right program if you search long enough. And it also because it's length sorted, you will fill this cup from the bottom up in a very smooth manner, and then you will find one. But of course it's inefficient, because nobody can afford executing all programs, and And the other is fixing a narrow representation with a narrow algorithm, but we've seen it's not possible. So actually we want some algorithm that there's this big Turing complete space and there's the solution at some point there. And you want to look at the task and then build an algorithm that looks at the task and then kind of incrementally narrows down where the solution is and then converges to that solution. If the solution is somewhere there, it should narrow down the task like this. And this is essentially what the theory of incremental compression does, which I'm going to present in the following. So when we describe stuff, in practice, we do it often incrementally. So objects have features like size, shape, color, and location. And when we describe an object, we usually enumerate those features and say what those features are. And if you look at some object encoding, for example, as a binary string, or it can be a string of integer, whatever, you can convert the data to each other. And then you specify the size. And then you map the description onto something where everything except the size is specified. So you sort of have split the description to the description of the size and everything else. And then you specify the shape and everything is except the size and shape. And so on. You go further. And then intuitively it seems that those features are independent properties in the sense that if you know the color, you don't know the shape, and vice versa. They don't have information about each other. And if features are described concisely, the full description will be concise as well. This is the intuition that I am going to substantiate. So the length of the shortest description would be the sum of the lengths of the descriptions of the various features. This is basically an independence statement. In probability theory, you have a multiplication. In algorithmic information theory, you have a sum. So in many respects, those things are a logarithmic version of each other. So I'm going to tell you for some slides about this general mathematical theory of incremental compression, and then I will argue that there is an exponential speed up compared to Levin or universal search, while it still remains quite general. Okay. So this will get a bit more technical, and I would like to know who is familiar with Kolmogorov complexity in general. Yeah, so quite some people. And I've seen it in the framework that those theories serve as kind of ground here at GoodAI too. So in case there's something unclear, please ask. So now I'd like to describe what happens with a data set that you want to compress, that you want to describe at a single step. So that's the goal. We want to find descriptions of data. That's the whole point of this. So so let's say you have that string to be compressed as a string of zeros and ones, and you look for a pair of strings which I call feature and descriptive maps, such that they are inverse of each other. So essentially, we're building an autoencoder. It's the formal specification of an autoencoder. And in algorithmic information theory, these functions can be mapped to binary strings. They have themselves a description, the functions. So you can essentially, functions or Turing machines, you can interchange with integers or with finite strings. There is a bijective map in all directions, so I can use those words actually, they mean the same. So I can actually talk of a length of a function or so. That means it's the length of the binary string representation of the function. And so what you do is you look for the shortest ones, feature and its inverse, the descriptive map, such that you have that equations solved, fulfilled, and you have to at least to find some compression. So that's P is the parameters, basically is what descriptive map maps here. And the new representation of your data set consists of the feature and parameter. So they together have all the information about X. And the condition is that you have to compress at least a little bit, at least 1 bit you have to compress. The new representation has to be smaller than the old one. And okay, anybody can set it up, and the question is this meaningful, is this useful, what does it lead to? The full compression scheme would be that, this is one step, and then you have the parameters, which is basically, you have mapped out some aspects of it, and the residual description, you keep compressing further. You find feature and parameter for P1, and so on. And since you keep compressing, at some point this process will end, and you will have finished. Let me give you an example. For example, the string is a 1 and a 0, 2 1s and a 0, 3 1s and a 0, and 4 1s, etc. So you could find a Turing machine that prints m 1s and attaches a 0. So the parameters that it would need to have in order to spit out the string would be P1, 1, 2, 3, 4, 5, and that you insert for m, and it will output that string. And then you keep compressing the parameter, which is another Turing machine that starts with P2 equals 1 and counts up. So this would be a two-step incremental compression. And as you already can see, finding those two machines independently of each other is much easier than finding the full description, shortest description of the whole string in a single step. And that's the intuition that, and I will also show formally that you will always get a huge acceleration. So, before you can do that, you can actually, you have to show that this compression scheme is actually leads you to the shortest description, because a priori that's not guaranteed, because you can do whatever you want with your strings and get some description, but will it be the shortest one? And now I'll tell you that it will, due to the following reasons. When you look for the shortest feature, the prefix Kolmogorov complexity, that's the type of complexity that I deal with here, is equals to the length of the feature itself up to a constant. That means that the feature itself is already incompressible. So you have that representation that consists of those guys, and this one is already incompressible, so you don't need to even try. And so you can compress that. But they could have mutual information overlap. And I show actually that this is not the case. So the information inside X is actually partitioned into the information inside F and P. And there is no overlap, and there are also no useless information. It's not like they contain some information that it's not in X at all. So there's no superficial, no information too much. Superfluous, that's the word. And so mathematically expressed, it means that the complexity of X equals the complexity of the pair, of feature parameter pair, which breaks down to the sum. That's what independence means. That's it's not. I will not go into the details of the proofs, because I mean, if you're interested, we can talk later. But that's what essentially means. The description length of your data set splits up into the description length of your feature and description length of the parameter that you then keep compressing. So, and I'd like to give you an intuition why this is the case. Well, you're looking for the shortest one. And if the feature and parameters contained common information, the feature would be made even shorter, because it doesn't need that information, that common information, because it takes it along when computing X. So if there's some information in both of them, and you put it together to compute X, one of them is superfluous. So you can make the feature even shorter. But since we have already chosen the shorter ones, there cannot be mutual information between them. So, and when you do that further, the information inside X, and if you compress then the parameters further into their feature and parameter and keep going, you will get to the sum at some point. At some point the parameter will be an empty string, and that means that up to additive constants, the sum of the length of the features is actually the shortest description. So that scheme actually gives you the shortest description. And that's guaranteed. You can do it greedily. You can find one, look for the next one, look for the next one. You don't have to track back. And mathematically, well, and then we can also show that those features that we have shown that those are independent. But since the subsequent features are all derived from those parameters, and they don't contain information about F1, the subsequent features also don't contain information about F1. And you can play the game with every pair of features and show that they don't contain information about each other. This is how it's expressed. It's a constant, but basically arbitrarily small when complexities are big. So essentially zero, it means. In that respect, it makes sense to say that the set of features is an orthogonal basis for the description of X. Orthogonal because they don't have information about each other. And they're also complete because you can actually compute X given the features. So this is all nice. We have shown that you arrive at the shortest description, but is this efficient? Is this any better than universal search or any other? Now I would like to compare. If you use universal search, it means executing every program of length of the k of the shortest program of description X. If you search like this, you have to execute 2 to the power of k of X programs, usually. So your program is that length, and you have binary strings. All binary strings of that length is 2 to the power. And when we look for a single feature, you have to execute 2 to the power of length of the feature. It's the number of programs that you have to try out in order to find it. And we see that on average it's the kth part of the complexity. K is the number of features here. And it's of course a lot less than 2 to the power of the complexity. So you will find a single feature much faster than the whole description. That's one thing. What about the descriptive map? Because in order to make a single compression step, you have to find feature and descriptive map. Because you don't look for the parameters by looping through all combination. You compute it with the descriptive map using X. And surprisingly, I managed to prove that its length is actually quite short. So it's essentially smaller than the logarithm of the complexity. So if you look for it, then you have to look for 2 to the power of the length, and it's of the order of the complexity. So it's the number of steps that you need to find it, and that's already very small. Usually you have to look for that. It's also the same comparison. So let's put it all together and see how many programs do you need to look through in order to find this all, to use this whole algorithm to find the final description. So here's the efficiency thoughts. So if you usually during a single step you look for both feature and parameter. You look through all combinations. So you have to use 2 to the power of the sum, and this constant comes from the descriptive map, and this is remains the same. And if then you repeat the whole process for every feature, and as I said, you can do it greedily, one feature after the other. So the number of programs is just the sum of those guys, up to those constants here. And so that's essentially the time complexity of incremental compression if you don't take into account the number of time steps of actually executing the programs. But this is a minor point. So now let's compare it to universal search. Well, recall that this equation is valid, and therefore, and if you put it into here, if you do it non-incrementally, you get a product of those guys, and incremental compression I've shown is just the sum. So you have big numbers which are multiplied, and here some you will get a big difference between those time complexities. And that is why incremental compression is much more efficient. And I have already 2 years ago I've implemented an algorithm that's not general, but it uses that incremental compression idea in order to find the descriptions of all strings that can be generated by Turing machines with 3 states or less, or 80% or so, or almost all. And so it actually works, and we're now developing the algorithm further, which Michael will tell you later about. So this finishes now the part where I introduced you the theory of incremental compression. And now I would like to relate it to Buddha's theory of universal AI. It's just one slide actually about it. Who knows about the theory actually? Yeah? Half maybe. Okay. I'll tell you about it because it's actually cool news. Because AI, for the first time, has an actual theory that is mathematically rigorous, and that shows that the agent that is implemented by the theory exhibits maximal intelligence. So there is no other agent that has more intelligence in the set of all computable environments. And that's quite cool, of course, for AGI. And I'll tell you a little bit about how it's formalized. So you have the agent framework, which is quite widespread. You have the agent makes an action, and the environment answers with a reward and an observation. Reward function can be fixed from outside, can be given by the programmer, and that defines what goals the agent is supposed to achieve. And then you have basically the agent and the environment are Turing machines. So the input to the agent is the tape of reward and observation pairs. So an observation can be anything. It can be an image, it can be a video, it can be a chess position, and whatever you might like. And the reward is a number. It's just a number, a real number. It gets the list of observation rewards, and it decides what to do, what action to take at every of the discrete time steps. And then the environment takes the action and then computes the next reward and observation. Two Turing machines interacting that way into each other. And what AIXI is the name of the agent. With this big formula, it's actually, you can put the theory at least this agent into one line. That's the surprising part of it. It's of course a big theory worked around it in the whole group, but it's good for explaining. So yeah, actually, so in time step k, you compute the action that the agent has to take. And what you have here is essentially what you do is you have a series of observation and reward pairs that you got in the past up to step k, and you look to the horizon to the length m and look at all combinations of rewards and observations that you might get in future. So you have a big branching tree in front of you. And for each of those combinations and the history, you try to find a program that computes it. and you look at all those programs and weigh those programs by 2 to the minus of their length. So essentially it means you look for the shortest programs, because the shortest ones will have biggest weight. And that's why you need compression for that, because you won't find short programs otherwise. And so you have that term, and what you want to maximize of the sum of future rewards. Remember, you combine through all of them, so you go through all combinations of observations and rewards, and want to try to maximize that sum. So it's clear then that if you look at the combinations where the rewards follow logically kind of from what you have already observed, if you can predict your own rewards, and also the states that accompany them or observations, then you will be able to choose the actions properly, if your horizon is far enough. And that's essentially what AIXI does. And the properties, it's incomputable. And if it even was computable, there are too many combinations to look into, because you look at all possible observations that you might get from your environment, and all possible rewards and all possible actions that you might take, and all their combinations, and then you find and then when you fix one of that combinations, you look through all programs that might compute that combination. So it's clear that it's really impossible kind of to use that directly. Even if you converse the whole universe to computronium, you won't be ready. But you can do it for very small environments with 2 states, 2 rewards or so. And the cool thing, it gives you a mathematical framework. When you talk about intelligence, it can get very vague depending on about who you talk to, and when you have the first good theory, then you can actually you have a point of debarkment. If you know what to relate to, it's like physics after Newton, or biology after the theory of evolution. And so one aspect of the work is at OCCAM we're developing faster approximations for AIXI. So how to make that work. And this is actually, I mean, I had a long history of ideas long before I knew about AIXI that convinced me that compressing data is really important, and AIXI is kind of a proof that it actually is, because you have to weigh all those combinations with short programs. I have not planned to give you the AIXI approximation, but if you like, I can do it later on, or there are additional slides for that. I did that because I think it's more relevant to get to relate that work to what actually you do. So, and let's move to that part. So we think that apart from provably leading to AGI via AIXI, the compression idea provides a unified framework to model many cognitive abilities. And for example, I've read some stuff on your page, predominantly the framework paper, and it seems that it's important for you to reuse skills which are quite broadly defined, and I might want to relate the skills to features, some kind of, it's a partial description or ability. And if we do that, so for example, why would we want to reuse anything at all? I mean, is there some systematic argument to make? And well, you have in universal induction, you have this universal prior, and for any string, you have some a priori probability that it might occur in the world, and also for you could say for all skills that exist, they might be an a priori probability that you might need it in the world before you have seen the world at all. A priori could see, okay, some Some elaborate skills are maybe less likely to occur. Some very basic are more likely to occur, and they are weighted by this factor actually. The simpler ones are more probable, the less simpler ones are less probable. But as you go in your particular world, this particular universe, AIXI is not dependent on our universe, it works on all universes. And there might be some skills that you need more. And so essentially you want to update that universal prior for those programs that actually occur more often. And then you have such trade-off. Okay, there are some skills that maybe I can remember them and in order to reuse them later, or I can look for them from scratch. For some simpler ones you might look for them from scratch, and some other more complex and frequently occurring one, you want to remember them. And in order to remember them, let's say you put them in a list or so. And the description length principle provides you a criterion to look them up. So if they're in the list, you need the logarithm of the index to look them up. It's the amount of information you need to specify that particular skill in the list of skills. And if you need it from scratch, then you have all sets of programs or skills that you might want to permute, and that also needs a particular description length in order to choose them from the set of all skills. And there's a trade-off, and that trade-off is actually computable by the description length principle. That's the point I want to make. It's kind of, it makes that decision, should I remember it or shall I save memory maybe and find it from scratch? You get a criterion to balance these things. Or let me give you an example. For example, naming things. Why do we name things like glass or monitor? Well, these are things that frequently occur in our environment, and if I want to, when communicating, I want to minimize actually the amount of information that I say, because metabolic cost, and you have to talk a lot if you don't communicate efficiently. And so you want to give somebody a piece of information that is sufficient so that he can retrieve the representation in my mind in his mind. So if I have a monitor in mind and I want that somebody else also has a monitor in mind, then I will tell him the name of it, if it's frequently occurring. If it's something not frequently occurring, I might give him a description. But I will tell you some more about it when I talk about language a bit. And also you can view, let's say you have this timeline and whatever you have seen in your past history. And when you do compression, maybe you have compressed some part of the history a little bit, and then you can choose if something reoccurs from the past history to now, maybe. So when should you reuse it? You should reuse it if the description length to find it in your own database is smaller than finding it again. But in other words, I have said it already. So the important part here, I think, is that for gradual learning and reuse, you need representations of arbitrary granularity. And this is something I would like to talk now about. May I have some more water? Yeah. There's a theorem that I found a year ago or so, no, half a year ago. So if you have two strings with the shortest x and y, to the shortest features f and j respectively, then either f will have all the information about j or none. This theorem is still kind of work in progress, but I think it can be finished. And look what it actually means. You have all sorts of objects and information inside them that describe them. And if you if you look at the shortest features that describe them, it actually means that they never intersect. They are either identically informationally or totally separate. And in that sense, it makes sense to talk of atoms. It's like objects consist of atoms that make them up, and then you can make other objects with combining the atoms in a different way. So, and it seems like information objects, or information in general, also consist of small pieces of partial descriptions. And if that's true, it's important if you want to apply a previously learned skill set, because if you have skills that are kind of very specialized and big and bulky, then you cannot combine them very well because they don't adapt nice. So you might want to have some big ones because they solve a task that frequently occurs, but it doesn't mean that you can decompose it then. So you should keep the smaller parts. It's like if you have a Lego and a construction set, you need actually small parts that are very flexible and can be combined. And that's why you actually need elementary features, these elementary atoms of information. That's why it's important to look for the shortest one, not just for some. And this is something I really would like to underline. So you can of course encapsulate some fixed combinations. You have some useful combination, make a capsule, put it into some block, reuse it, but you have to keep the atoms too. Now I would like to, this will be relevant in the following, but I would like to say some words about gradual learning. And this is not really precise, but I'd like to get some intuition across that I have about these things. And it looks like many data sets in the world are power law distributed. So you have English texts or music of Bach or the human genome. And could it be that the world is something like a complexity fractal, where in fractal you have always those power laws? Meaning that it looks like wherever we look at the world, and if we zoom in, we always find some structure. And if we zoom out, we always find some structure. Maybe the world is actually structured in such a way that it by itself proposes an optimal environment for gradual learning. If you can kind of select by varying your attention to various parts of the world, if the world is structured in such a way that it always presents you a challenge of the right complexity, that is actually, or of arbitrary complexity, then you actually already have the perfect environment that you need so that your agent can learn. And do we have evidence for that claim that the world might be structured like this? Well, as it turns out, those power laws that are characteristic for that scale-free behavior can actually be generated by a hierarchical compression scheme. So if you instead of this linear non-branching thing that I presented earlier, if you make it branch, you have a piece of information, some uses one piece, some uses another piece, and it branches. And it generates your data set. If you generate data sets in such a generative model, it automatically installs those power laws inside them. That's what I've shown formally. So the information between two pieces of x, xi and xj, is bounded by the complexity of the highest node times the distance between those pieces and to the minus of a constant, which is a power law. And the constant just depends on this whole architecture, how much information you lose when you do that. So the interesting part of it is that if you have those partial descriptions of your whole data, let's say X is the whole universe or so, you don't need to find features of the whole universe. You can find features of small parts of it. And if it's scale-free, if you can zoom in arbitrary far, that means you can find features in arbitrary small pieces of your data. And that means you can find regularities in arbitrary small pieces of your data. And that's what actually enables you to understand them. Actually, if you find regularities everywhere that you haven't found before, it enables you to learn. Where is my water? So it may be, I don't know it, right? But it may be that tasks are automatically spoon-fed to us by our world, our universe we live in, at the right difficulty by this complexity fractal. And that may be even a criterion for gradual learning. You have your knowledge base, all you know before, and you have your data set. What you want to find descriptions of of your data, given what you know, and if it's small, then you can learn it efficiently. But you have got much more elaborate thoughts on these things. So it's just ideas and associations that I as for this criterion that I have here, and the thing is, we don't know how to construct an environment that is a complexity fractal actually, and people have tried it to do these things, and it's especially interesting to learn about the history of artificial life. So the research area where they make genetic algorithms that evolve. They hope to evolve complex creatures. And this whole field has been a failure, I'm afraid, and it's not very famous. And the reason is that the creatures that evolve, they don't get very complex. I mean, it's interesting to look at evolution, but it's not like there's an open-ended increase in complexity, let alone some intelligent creatures or so. Nobody has achieved to evolve that. So maybe it's due to the fact that they are not able to put them into an environment that enables them to increase in complexity and to learn gradually. Maybe we are not able to simulate those environments in the computer because we don't know how to create them, these complexity fractals. So, yeah, I would like to discuss these things with you. So, yeah, this is related to this atomic story that I presented before. Sorry, it's a bit potpourri of various thoughts and various aspects that I find important. So, before I stressed that you really need to have those elementary atoms or elementary pieces of information to represent something in a really flexible way. How does it work with in machine learning in general, or let's say in neural networks? What you get? Well, actually, there's a quite nice match between the incremental compression theory and deep learning, especially for deep belief networks. So what you do in deep belief networks or feed-forward networks in general, you have this composition of functions. So if your data and compose it layer by layer. It's a composition of functions in elementary and mathematical terms. And what the functions that we use here are called descriptive maps. In neural networks, it's just a single layer of networks, of a network that does the map of the input to the first hidden layer. And so you can compare them. We look for arbitrary f and f prime, and in neural networks, it's a particular function. So you have the weight matrix multiplied by your input and put through some nonlinearity. And it's basically a parameterized family of functions. And it's parameters by the weights. And then you do the search through the weight space and then find your solution. And in deep belief networks, you have the inverse function too, in a feature in our words. And so you have these stacked autoencoders. The problem is that if you look at the complexity of a single layer, it's very high, because you have arbitrary weights in them. You have a big weight matrix. So, and the complexity is roughly the length of the whole matrix. So it's basically the number of numbers that you have there. And it's very big. And what our theory shows, that in order to compress well, in order to arrive at representations well, you have actually to find the shortest one. And this is something not really done by neural networks. And if you think about it, it's a big problem in machine learning in general. So you have these spaces and you wander around them and solve optimization problems. And those spaces, the elements of those spaces have high descriptive complexity or chromograph complexity. And therefore, a priori are not likely to be a good solution. Because of Occam's razor, that's what the whole deal is about. And that's why we live in the area of big data and in the world of big data, and no one-shot learning is not possible, and these kind of things. That's the big problem, and because there's no simplicity bias. And we don't, of course, I'm not the new one, the first one to notice. Of course, people have regularization techniques and dropout in neural networks and a myriad of techniques in order to decrease the size of the representations, but they're very bulky, or they're very rough. For example, often they try to minimize the number of parameters. But there are simple sets of a large number of parameters. For example, if every parameter has the same value, it's simple. The descriptional complexity is small. Yeah? But there's no bias inside optimization techniques that actually helps you find that simple combination. In convolutional neural networks, you build it in by hand because you have those batches, and every batch has the same set of weights. But it's built in by hand, and you would actually want to have an algorithm that finds it by itself. So it very much relates to the aspect to have these smallest atoms rather than big parameterized representations. So I'll skip that one. So now I've discovered this slide in your talk, and you list some learn general abilities. I would like to go through some of them and kind of highlight it's not like we think we know a solution for everyone. So the green marks mean that we have some ideas. So I've talked already about induction and feature selection. There's the other points, for example, logical reasoning and deduction. What about deduction? Of course, there's this big problem of logical reasoning in AI in general, right? You have formal logic or classical, non-classical, various logics, and then you have systems that do perception and motor learning and stuff like that, more low-level stuff. And there is this big gap, which is known as symbolic and sub-symbolic gap. So you have these symbolic kind of logical reasoning systems, and it's hard to attach them to the perception and motor systems. And here's essentially our approach to it. We do not have a separate layers of reasoning and perception. It's all one data set and its representation. It's automatically grounded, meaning that your representations are connected to your data set in the sense that it's a generative model. So you can generate data using your model, and you can also generate descriptions by running them this whole. So there's a back and forth between your representations and your data. It's automatically grounded, and so the description direction is called then induction, their generative direction deduction. In what sense? Let's give you an example. Let's say you have a triangle, and if it has equal side lengths, then those two angles will be the same. Simple theorem from geometry. Can we use our formalizations to make that conclusions actually? Oh, it turns out we can, and without using formal logic at all. How does it work? So there's a theorem that I've found. Let's say you have a string and you have two features, f and g. In our example, f may be the features of sides having equal length, and g is the feature of equal angles. And then P is then everything you need to know about the triangle apart from equal length. And this is Q is everything you know about the triangle apart from equal angles. And meaning the exact length and the position of it, orientation. And what I've shown is if G doesn't know anything about P, those guys, then the information about G will be totally entailed in F. That expression means that you essentially don't need additional information to create G from F. And that means that, in other words, the G follows from F. There's no new information that you get from G if you know F. And that's what it means that equal sides entails equal angles. So essentially, if you have two possible representations of your triangle, and if you can check that the information inside G is fully inside F, you can claim it that it follows from F. But you have to ensure that those guys don't have information about each other. What does that mean intuitively? It means that all other stuff you need to know about the triangle is not related to the specification of equal angles or so. Essentially, it means if you draw random triangles, so you put random numbers here, you get here random triangles that have equal side lengths. They will, and if you have two random strings, G and P, or P is random, then the probability, the expectation of their mutual information is quite low. If you do two random strings, it's very low probability that they have mutual information. So that means this will be a zero with high probability, and the theorem works. So intuitively, what does it mean? If I draw a triangle with two equal sides, and if it has also equal angles, and if I make it 10 triangles like this, well, chances are that it follows from it. That's the formalization of that intuitions. So essentially, if we go into the tradition of psychological theories, it's part of the simulation theories. So simulation theories describe that we reason actually by simulating the world in our mind. And if I tell you, okay, imagine a triangle with equal sides, and you simulate it, and look at a particular one, and you discover, oh, it has equal angles as well. And you look at other ones, and then you conclude, oh, well, maybe that's always the case. Yeah? And if certain conditions are met, this is actually guaranteed. The cool thing about it, you don't have to set up a knowledge base like it's usually done in logic-based approaches. So you have to code all the knowledge and all that stuff. The information that you need to make that inference is actually inside your data itself. I mean, it's somewhere inside the data that it's actually an implication from equal sides to equal angles. And by doing proper compression, you can make that inference. You can even discover that it's like, for example, I draw you a triangle with equal length, side length. Then you will, if you draw some and find a short representation, you will discover that one of the particular representations actually assumes equal angles too. So if you don't have to put into your database that from A follows B. You can ask them, okay, you have A, what follows from it? And you can discover it inside your world. And that's why it's much more powerful than usual logic-based approaches. You can actually discover what's true by interacting with the world itself, And you can escape from that exponential blow-up of knowledge bases that you get in logic-based modeling. Okay. So here's imagination is the simulation part, by the way, reasoning deduction. So let's talk a little bit more about language. In cognitive linguistics, there is this prompt theory, and it says a language merely provides prompts for the construction of the conceptualization, which is far richer and more elaborate than the minimal meanings provided by language. Well, what it means is there's this tradition in linguistics where people try to think that every word in a sentence has a separate meaning, and the meaning of the sentence is somehow a composition of the meanings of the words. And there are many examples where it turned out that it's not true, it's too simplistic, and it rather looks like in this prompt theory that we say just enough to get the right information across, and it's not in the word itself; it's in the whole message itself. So the proper formalization would be actually to use algorithmic information theory and compute what string I need to convey so that you know what I know, and what's the minimal length string that I need to transmit. And that's the perspective on language by information theory. And let's say if I tell you that a triangle is a figure that is connected by 3 lines. That means I have a theory of mind. That means I have an assumption about what you know. I assume that you know what lines are and what number 3 means. That's your representation. And I have my own. And I'm thinking of a triangle. And then I compute the residual information that you need to know in order to get the same thing. Okay, the 3 lines, you have to connect them somehow. And then you also know what I know. And that's something you can compute. It's a conditional. It's described by conditional Kolmogorov complexity. And there's a whole field of communicational complexity also. You can study these things. Yeah. Well, let's skip that. It's not that important. Okay. So that doesn't mean that I've solved anything with language, or so it's a huge field and it's just a little perspective, okay? Attention and curiosity. Well, of course, there are many things that draw our attention that are not immediately related to intelligence. Like there are emotional and evolutionary biases. We prefer to look at faces. We look at the people who might be aggressive with us, or people who want to mate with us. These are the preferred targets of where we look at. But if we detach the emotional and evolutional aspects and just look at intelligence, what might draw our attention? Well, if we want to learn in an open-ended, gradual way, we want to notice where are those parts of the world where I can learn something actually. And this is actually verified by experiments with infants, for example. If you give them some sequence of flashing stimuli on the screen that's flashed left and right, infants have a preference for moderate complexity stimuli. So if it's too complex, they look away quite quickly and start crying. And if it's too simple, flashing only on one side, then they get bored. And so it looks like attention in infancy is complexity driven in the sense that what next problem is not boring and I still can solve. So now let's talk a little bit about metacognition, because then it relates to our algorithm that we actually started to build. So metacognition is cognition about cognition, as the word says. It relates to representing your own representations. And the main idea is if you understand a wide range of data and can achieve goals in them, in them. Then you will also understand yourself, because you can encode your internal representations into data. And so if you have a framework that's simple but general, and if you have some encoding, internal encoding, that has found some partial description, that means the description length of the encoding will be simpler than your original data. So let me tell you that again. You have, maybe it's better in the context of the algorithm. Let's say you have a program tree that you want to search through the multiplication here, and you have at the nodes some numbers, and it means a factorial. It multiplies 1 by 2 by 3 by 5. And it's the representation of the factorial. And then if you encode that tree into a string, that means multiply, 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 and then 1, 2, 3, 4, 5. It's just some tree encoding into a string. Then you can use, again, that tree, the algorithm that looks for trees, in order to compress that representation. Now you can compress it, or then you can also generate other trees, vice versa. So then you have a meta representation of your tree. What it means if you build an algorithm that can represent a wide range of data, and that algorithm compresses your data already a little bit, then the representation that it uses to compress will be simpler than your original data. And if you encode that representation, your own algorithm will be able to compress it even further because it has become simpler. So we have actually started to do that. To apply the algorithm onto itself. It goes into the direction of recursive self-improvement. Because often you have, of course, if you look through all sorts of programs, you will get into combinatorial explosions. That's what I mean, we want to build it in order to compress data, and but we don't know, well, how shall I say it? You would actually find smaller representations, but in order to measure the size, you need to compress and measure it. So it's kind of a hen-egg problem. You need the compression algorithm in order to build the compression algorithm. So that's why we use it iteratively. So first we feed it with some heuristics, run the algorithm, and then help the algorithm so that the algorithm helps itself. And there's an example where it's quite useful. For example, you have this tree and you have those nodes, and you have to go through all combinations usually of numbers in order to find whether it satisfies some target. But if you can create your own, can use your own algorithm in order to satisfy this condition with some simple ones. If you generate some simple combinations, then you're much more likely to find a solution actually. So we use our own algorithm in order to reduce this combinatorial explosion. And that's actually, I think, one of the main things that this monolithic algorithm should achieve in future. It should, when applied to itself, avoid this combinatorial explosion problem, the curse of dimensionality. Michael will tell you more about how the algorithm works.
So yeah, take a deep breath. It's getting easier from here on. We just started to implement that stuff like end of last year. So it's still like we're on the first building blocks and puzzling them together. So the first building block is actually to find like a representation for a single feature. So a single feature could look like this, or like a data. And what features do we find in the first sample data? Okay, it's a bunch of ones and it's just repeated 8 times, so it has a length. The other ones, it's a sequence, it's just increasing all the time, so it's always increasing element by element, it's always increasing by 1. The stuff, okay, we could find like some easier representation for that. And the simpler representations are here. So we find simple programs. I don't know who's familiar with Python, so we don't need most of you, no? Nobody, okay, a bit, yeah. We need a list with like one element and we repeat it 8 times. We could also find a different program that gives us the first list, which would be like take a 1 and put a minus there and put a minus there and make a list out of it and then have something else added together and then repeat it. Which would be a representation that comes up when you just search broadly through some tree, but it's like the representations that we actually try to avoid to find, or like because we just want to end up with that stuff, and it can even go worse and you find like, okay, let's convert it from 1 to 1, and the more options you give your search, the more you will end up with that stuff if you're not careful. So the other options are easy. Okay, we have a program that just increases our sequence and produces the sequence right away. We just need to find the length for the sequence. And for 0.2, we can say, okay, easy, yeah, let's divide it by 1.5, but it's already something that probably shows more information than the 0.2. And here is a sequence, okay, you already need to build like a tree with like a bunch of nodes, 2 or 3 iterations that you say, okay, I have a range, it doesn't start with 0, so it needs 1 parameter, and it needs like some end, and then you need to do some conversions on every single element. So how do we come from, when we look at target data that we kind of want to express, how do we kind of construct these trees that we want to find, that actually describe these features? Yeah? So these are shorter descriptions than there. And we try to, we start with like building a tree. Yeah? In our mind it's like rather, we just go and say, okay, yeah, it's a logic, and then we just write some program code, but how does it happen? Yeah? So with our algorithm, we just start with a single node. The single stuff is like, okay, top node, do we already have the result? If it's like, okay, if I just want to find like the number 5, okay, I don't need to write a program for that, it's already there. So it's like we have input nodes, and if we don't have the proper result, okay, then we need to like extend the tree step by step. So the representation is like we have function nodes and we have input nodes, and that's already how it combines. In the alphabet, we actually quite have a long list. It goes even further. We have like simple inversions, nodes that just negate, divide by itself. We have nodes with like several inputs and or add, sub, multiply, and we have more complex operations, like for example, if else you put 3 arguments there. So we try to express everything as like a function node, and then so it means like it can be one arrow here or like 2, maybe even 3 at some point. Also, like you have to be a bit careful, like for example, like this multiply, it's not only like a multiplication of like integers. Yeah? So you can multiply integers with it, you can multiply floats in Python, you can also like multiply a list with an integer. So basically all of these functions, they not only, all of them have like a kind of type specification that you can throw in there. So it's the alphabet is yeah, kind of multiplied by all the options of types that you can throw in there. And yeah, when we start to build these trees, like we go with a single element first. Yeah? So we have a bunch of side conditions that we have to take care when we start to develop the tree from one element and grow it and grow it and grow it. So what do we have to take care for? Yeah? One of the first story is like that the data types are correct. Like if I'm looking for a list and I have a function that produces integers, yeah, that's pointless to put a node here that produces integers when I'm looking for a list afterwards. So I have step by step, whenever I kind of extend the tree, I have to keep in mind, okay, what's the type that I actually expect? Yeah? If I just puzzle all the trees together without looking at the type, the explosion of the space will be just like even more than it is already anyways. So I have to look at like my input data. I see the types, and I have to kind of iterate the type through the whole tree. So when I have a list of integers here, okay, I'm looking for functions that produce a list, and I know like the list is expecting integers. So I need to represent all that stuff in some typing system. It's not only types actually, because like sometimes there are functions that, for example, range. When I put like a -5 in there, it just produces an empty list. And if I put in -10 in there, it still produces an empty list. So basically I want to tell him, okay, I just need positive integers there. Or like for other things, I am expecting values from an arbitrary range between 0 and 1 or whatever. So I have like other value range conditions that I also want to inherit as good as possible from step to step. And I also want to try to avoid redundancies. For example, when I know here, okay, I just had a node with like, which kind of puts a negative sign on it, and I do that again afterwards. Just as we saw before, then I'm still producing a valid tree, but it's completely meaningless, or it's just like much more complicated than it was already. And secondly, when we kind of build the trees, we try to build it like with increasing complexity. And that's actually the hard part, because like we don't know in advance how complex a tree is when we just put another node in there. So we try to approximate this for now, for like this first step, by building the trees with increasing description lengths. And we can guess the description lengths rather well, because we know, okay, this is an input. It has a certain length, okay, it's an integer, and the log of the integer roughly gives us the description length. We have an operation. We can look it up in our alphabet or in our function storage. And so we also can basically, it's the log of the length of our alphabet that we use. So we just add all of it together, and we have the final description length of that part. So that part knows its own description length. And that node can just ask this one, okay, what's your description length? And then say, okay, when I want to exchange one of the nodes, which one is giving me the shorter description length? And so this node here can decide between like, okay, all this type specifications that he finds valid, in our alphabet. We put them in a registry for all type specifications. So we can look up, okay, I need some function that can produce this valid input, that can produce this output. And from this type registry, we get a long list of possible function nodes. And these function nodes again define, okay, I need this kind of input nodes, and then the nodes kind of produce like different subtrees, like in 2 dimensions actually. So it's a bit vague. I should have put like some more effort to make some proper graphics there for that. But in that way we can iterate through the different trees with like kind of guaranteed increasing description lengths. And we want to improve that further in the future by actually like applying this algorithm of compression like on its own again to compress the trees, and then we have a better measure for complexity, which means like our own compressed code for like that very tree. So and then we can make the sorting or like the searching hopefully even more effective in terms of how many lookups it needs. Of course, like on the cusp of like run complexity maybe for every single iteration of the tree. The typing system that we use is like standard Python 3 typing stuff. So we have lists, for example, and they are kind of guaranteed to have like always the same type. So I have a list of ints or I have a list of floats. Tuples are like kind of data types, like structs maybe in C. And so the types that we get out or throw in, they don't even have a real name. Yeah? So it's the program is supposed to be able to create its own types and just throw it together, puzzle together, whatever it needs there. That's also like still like we're not really happy, for example, with how we present like the conditions. That's one of the topics that maybe someone else also has like some clever idea. That's what we're discussing internally right now. And they can be composed on the fly. That's what you saw here. So some examples from what the testing and what the program currently spits out. So it gets the task to explain 289. So what does it find there? Is it? I mean, it's like some firstly seemingly maybe random integer number, and maybe there was like some deeper meaning behind it. And so we see it finds, it can it can take some numbers, put some minus sign in there, and when you do that with 17 and 17, you get it. So it's square. But it also finds like all the other options there that you have, like whatever converting forth and back. Why does it find it? Because we don't stop when we find the first solution. So when we find the first solution in the tree, at least we get like the good description length now. That is, but it still doesn't stop at that point. It keeps further searching, and then you end up with that stuff, and at some point you just cut it off and say, okay, there is no sense in like looking further for like very long stuff. And it also can spit out here, for example, the first just thing that we had on the first slide, the combination with the join and map and string. So it's right now we get like to level tree level of 3 to 4, which is rather not impressive. We didn't really try to optimize anything for parallelization or stuff. So the problem is like right now it's like rather early on with all this algorithm and like doing like mathematical improvements or improving like the way it searches through, or like adding in extra constraints where it should not go to, and suddenly it's like 100 times faster. So, and as long as it's like still in that way, we don't really want to put effort into scaling it out, because like one small improvement here and we go further with that, but it doesn't help us to have like extra complexity for parallelization or like for using some cluster somewhere. So the future steps is definitely the encoding of the conditions, which I already mentioned. We're still a bit like not clueless, but like experimenting forth and back how we really want to handle that. The restrictions like, okay, it should be a positive integer, or it should be like a single value, or it should be a triangle with same sides. The optimal partitioning of the data is another option. For example, if you have a sequence like 1, 2, 3, 5, 5, 5, 5, 5, 5, so you see like it's ascending, a range first one, and then you have just like a repeating value, and it's clearly like split in two parts. So it's obviously it's partitioned, and we have some algorithm who is kind of like just trying to find like some patterns there. It's not really efficient. So something nicer would be good there. We are implementing like to like increment the incremental compression part. So it means like after we found like the first set of features, then to iterate it further. And we are still experimenting with different ways to properly save the functions and reuse what we found there. So which means like building a memory or like function memory. There are a bunch of mathematical questions to how to do like a correct biasing. For example, like some operators will be more frequent than other operators. So we kind of want to start our search in the tree space when it was like, for example, multiplication, adding something, subtractions, like simple mathematical operators, and we probably don't want to start with sinus functions or like other more complex mathematical stuff, but how to properly bias that stuff one against the other. So right now they're all kind of like on the same level, and we don't really have a good mathematical approach how to say how to justify to use that one first and the other one after. So we maybe want to do statistics, but maybe we find something better there. Yeah, stories of functions. We try to get a demonstrator running, a proper one, for the next presentation in summer in Prague. Yeah, I guess. So summarize, please. So to summarize the approach, it's a monolithic or homogeneous approach to AGI. Meaning that we try to build a single algorithm or maybe some additional, but I think that's important from the perspective of recursive self-improvement and metacognition. It has to be an algorithm that can use its own representations as data and then describe it. And if they are very diverse, I imagine it can be quite difficult.
And also the difficulty if you have many different algorithms to build interfaces for that. But of course, it's the whole approach of cognitive architectures, and who knows what's better. I mean, so at least that's how we approach the problem now. And so as I've described, that the solutions or ideas for solutions to various cognitive functions and abilities emerge as special cases in resource-bounded settings. So you need to have some efficient memory because you don't have an infinite amount of it. And the whole theoretical justification of this approach is that we actually have AIXI that shows us that doing proper compression will lead to artificial intelligence. So we have that theory under our basis. And now we really want to move forward to develop the algorithm further, actually to build a practical demonstrator, which we haven't yet, that actually shows those cognitive abilities. And yeah, we're here, and we're happy that you have invited us, and we have talked to Jan at various meetings before, and we had the impression that there's quite some overlap between what you do and what we do, and we hope to be useful for each other, and yeah, exchange ideas and maybe even collaborate at some point. So yeah, thank you for your attention.